Okay, good morning everyone and welcome again to ECNG 1060. So today we'll be looking at a tutorial based on stuff that we did last day in class. And then hopefully if things are completed within a reasonable time frame, we could go back to the lecture. And we don't have much again in terms of the lecture. So hopefully if we don't complete the lectures by today, we will definitely do so by Friday, right? And then the rest of the time is just to look at questions and so on in preparation for your midterm and your final exam. So I know by now everybody would be doing what they need to do in order to prepare themselves for the midterm, because you know already where you're being tested up to in terms of the midterm. Nevertheless, we have to continue in order to finish up the course so that you'll have enough time to grasp and practice the material in order to do well in the exam. So I'm going to share the screen now, right? All right, so these are some practice problems here on the on periodic functions, right? So this would not come in the midterm, but it would definitely come in the final exam, right? So since we covered this stuff last day, we look at some of the problems here. So you're getting hang in doing problems of this nature. So this is 46.1, right? From the Finan text, find the Laplace transform of the periodic function whose graph is shown, right? So you're looking at the graph here, right? So you notice the graph between 0 and 1, it is 3. Between 1 and 2 is 1, right? And between 2 and 3, going back to 3. And between 3 and 4, it going back to 1. However, between 0 and 1, on the left end point, you see the circle shaded, meaning it includes 0 here, right? But on the right hand point, the circle is unshaded, meaning it doesn't include, right? So from the graph, we observe a repeating formation after 2, right? So you see between 0 and 1, the graph is 3. Between 1 and 2 is 1, and then you're repeating 3, then 1 again, 3 and so on, and then 1 again. So from 0 to 2, after that, you see a repeat. From 2 to 4, the same thing occurs and so on. So it means that T is 2. Capital T is 2, meaning the period, right? So this is one way in order to identify the period in the graph, how long the period is, right? So if we look at the definition, right, of the Laplace, you take the limit, the integral of between infinity and 0, e to the minus st of the function ft. Now, we know that this function is piecewise, right? Because between 0 and 1, it defined to be something, and between 1 and 2, it defined to be something else, right? So therefore, you have to break it up. So you see the integral between 1 and 0, e to the minus st, the graph is 3, so ft is 3. And between 2 and 1, right, the graph is 1, ft is 1. So you break it up into these two integrals here, right? And then you integrate. So this part here, you'll have minus 3 e to the minus st over s, and you evaluate that between 1 and 0, right? And then the next part here, minus e to the minus st over s, and you evaluate that with the limits 2 and 1. Right, so if you put in 1 here, you'll have minus 3 to the minus s over s. Right, so I write that as the second term, and if you put in 0, you'll have minus 3 e to the 0, which is 1. So you'll just get 3 over s. So I write that in front. right? So I'll write the positive term in front, and likewise it will happen here with this other part here that we integrated. So you'll get e to the minus s over s when you put in the 1 here, because it'll be minus minus e to the minus s over s, which is e to the minus s over s. And then when you put in the upper limit, you'll have minus e to the minus 2s over s. Right? And then we could just simplify this minus 3 e to the minus s over s plus e to the minus s over s. These two terms are like, you could combine them, so you'll get minus 2 e to the minus s over s. So this is the answer here, 3 over s minus 2 e to the minus s over s minus e to the minus 2s over s. Right? And then we recall, if f t is periodic with period t, the Laplace would be the integral between the period and 0, e to the minus st ft over dt over 1 minus e to the minus s capital T. So therefore, all you have to do is take this here, this result, right, that we obtained by finding the Laplace of ft, and divide it by 1 minus e to the minus s t, right? So which means you'll get 3 minus 2 e to the minus s minus e to the minus 2s, right? All over s divided by 1 minus e to the minus 2s, which is this term here, 1 minus e to the minus 2s, right? So that is how you evaluate the Laplace of this piecewise function, that, well, this periodic function, right? Remember that this is the Laplace of a periodic function here. This is the formula. Any questions on that? So we could move on to another one now. Okay, so 46.2. Find the Laplace transform of the periodic function whose graph is shown, right? So again, look at this here. Between 0 and 1, the graph is 2. Between 1 and 3, the graph is 1. Between 3 and 4, the graph is 0. And then you see that repeat again. So clearly, you could see that the period going from 0 to 4. And then you see another period here from 4 to 8 and so on. So they repeat information after 4. So they mean the period is 4, right? So now if you want to find the Laplace transform, you have to break up this, you have to use the definition of the Laplace, right? E to the minus st ft between infinity and 0, and then you have to break it in the periodic function into the pieces here. So you'll be taking the integral between 1 and 0 when the graph is defined to be 2, right? The integral between 3 and 1 where the graph is defined to be 1, and the integral between 4 and 3 where the graph is 0, right? So of course here that this part here will come out, right? Right? So this part here with the 0 would come out. So just these two parts here would survive between 1 and 0 and 3 and 1. So therefore you just integrate this here, which is minus 2 e to the minus st over s. And you take the limits here, 1 and 0, and then the other part here would be minus e to the minus s over s. And you take the limits here, 3 and 1. So from this first part here, when you plug in the limits here, you'll get minus 2 e to the minus s when you put in the 1 over s. And when you put in the 0, you'll get minus 2 over S, which is 2 over S. And then the second part here, when you put in the 3, you'll get minus e to the minus 3S over S, which is this term here, the last term. And when you put in the 1, you'll get minus e to the minus S over S, which is positive e to the minus S over S, right? So it's just a convenient way of writing it, putting the positive value to the left and the negative value to the right. If you want to do it the normal way, no problem. It's just my way of writing it because I find it easier to see it in this. It looks neater then, right? So now we could simplify here. The two middle terms could combine. If you look at them, both of them are e to the minus S over S in them. So you'll get minus e to the minus S over S when you combine these two, right? So the Laplace here will be 2 over S minus e to the minus S over S minus e to the minus 3S over S. And then from the definition, right, the Laplace of a periodic function would be this here that we just worked out, divided by 1 minus e to the minus st. And we know that the period is 4, so it will be 2 minus e to the minus S minus e to the minus 3S over S into 1 minus e to the minus 4S, right? So we're looking at another one here again. So we have find the Laplace transform of the periodic function whose graph is shown, right? So let's look at this graph here carefully. When we see a repeat, we see a repeat here, see a line here from 0 to 1, then the graph has a slope here between 1 and 2. And then you drop back down to 0 again between 2 and 3, and then it slope up from 3 to 4. So of course here, it will tell you that the period is 2 because after 2 you have a repeat, right? Now, so you're taking your definition of the Laplace transform of your function, e to the minus S between infinity and 0, ft dt. And you're breaking it up between 1 and 0. Well, of course, here between 1 and 0, the function is 0. So this part here won't give us any contribution, right? It's just, it might be just convenient to write it so you will see that there. So you won't forget. And then between 1 and 2, right, we had to determine how the graph is defined here. Well, if you notice here, the rise, we could find out the slope, right? So that is the slope there. The rise over the run. If the rise is 1 and the run is 1, right? Of course, 1 over 1 is 1, so the slope is 1, right? So the slope here is 1. And now we want to find the intercept because this is a straight line, right? So you have y minus y1 equal m x minus x1, right? Just straightforward. The slope is 1, so you could use either this point here or this point here. So this point here is 1, 0, and this point here is 2, 1. So if you have y, let me use the 2, 1. Right? So let me use the x is 2, y is 1. Right? So y minus 1 equal m 1 x minus x1. So this will give us x minus 2, y minus 1. So which means y will be, you carry the 1 here, that will be x minus 1. Now remember, our function here is a function of t, right? So this, your y-axis is actually your ft axis, right? And your x-axis here is your t-axis, right? So which means you'll just change x to t. So that is why you get t minus 1 here. So this is a nice, easy way to figure out how the function is defined within certain regions. You understand? Right? So this is t minus 1. So this is what we'll have to evaluate. So from this here, we could break up this into e to the minus st by t minus e to the minus st, right? So you have two integrals here, and then this part here we integrating by parts, right? So you call the t v, and you call the e to the minus st du, right? So from that you'll get dv is 1, right? And you'll get u will be what? E to the minus s over minus s. So we're using this fact here then. So here is uv, right? So that is these two terms here, minus t e to the minus st over s, right? And then you're subtracting u dv. So that will be this here. So you're subtracting this, so you'll have a negative, which will give you a positive. 1 over s, you could pull that on the outside, right? And that will give you e to the minus st dt. And then you have to subtract this integral here, which is e to the minus st between 2 and 1, right? So from this part here, you'll get minus 2 e to the minus 2t over s. You write that second. And with the 1 here, you'll get minus, so that'll be e to the minus s over s, right? And the 1 over s here, when you integrate here, you will get e to the minus st over minus s. So I put the minus s inside, and I multiply by this s, so I get e to the minus st over s squared, evaluated between 2 and 1, minus e to the minus st over, minus e to the minus st over s, because this s here will be negative, between 2 and 1. Right, so here now we write back these terms here. So the second term here will be the first term rather will be minus e to the minus 2s over s squared, and you get e to the minus s over s squared when you put in the 1 here, because our minus will give you a plus. And then here now, right, you could pull out this negative here, and this will give you a positive, right? So that will give you e to the minus 2s over s. And then with the negative term, it will be e to the minus s over s. That is this term down here, right? So you have 1, 2, 3, 4, 5, 6. And we could look and see if we have any like terms, right? We have this one here and this one here. Sorry. This one here and this one here. So minus 2 plus 1, that is minus 1, right? So that will be minus e to the minus 2s over s from these two terms, right? And then here we have this one here and this one here will cancel, right? Because this one is positive, this one is negative, and then you'll have these two here, e to the minus s over s squared minus e to the minus 2s over s squared. So therefore, we could make s squared the LCM, so we'll have to multiply this third term here by s. So you'll have e to the minus s minus e to the minus 2s minus s e to the minus 2s over s squared, and then the Laplace transform now of this periodic function. Remember that the period is what? 2, right? So all you do is you take this here and you divide it by 1 minus e to the minus 2s. So that is the same as e to the minus s minus e to the minus 2s minus se to the minus 2s over s squared into 1 minus e to the minus 2s, right? If you want, you could further write it like this here. You could factor out e to the minus s, and then you'll have 1 minus e to the minus s e to the minus s. So you could pull out e to the minus s as a common factor if you wish. Just for a little more completeness in terms of writing the answer. Find the Laplace transform of the periodic function whose graph is shown, right? So once again, look at it carefully. So again, we see the period is 2 because you see now a straight line here with a gradient between 0 and 2. And then the same thing happening between 2 and 4, and between 4 and 6 and so on. Right? So we need to find the gradient of this, but this gradient easy because the rise here is 2 and the run is 2, so the gradient is 1. And the y-intercept is going through the origin here. So it means that this function here is just t, right? So we take the integral between 2 and 0, e to the minus st by t dt. Right, and we did that already. So you're integrating by parts here, right? This is dv, and this is u, right? Let me see what I call it up here. Sorry, I call it v and du, right? And we try to be consistent, right? So this is your du, and this is your v. So again, your uv will be minus t to the minus st over s, and then your minus, which will be 1 over s. You pull it out on the outside, the integral between 2 and 0, e to the minus st. And then you plug in the limits here, you'll get minus 2 e to the minus 2s over s, and then minus, right? But remember here, you're substituting t equals 0, not just in the exponential position, but here. So what will happen here, once you put in t equals 0, this will drop out. So you won't get any other term from that. And then from the other integral, you'll get e to the minus st over minus s, which is minus s squared in the bottom. So when you put in the upper limit, you'll get minus e to the minus 2s over s squared. And then from the lower limit, you'll get plus 1 over s squared. And the LCM here is s squared. So this term here have to multiply by s. So you get 1 minus e to the minus 2s minus 2s e to the minus 2s all over s squared. And then you have to divide this by 1 minus e to the minus st, which is the period. So you'll have 1 minus e to the minus 2s minus 2s e to the minus 2s over s squared into 1 minus e to the minus 2s, right? And we could write this here as 1 into 1 over s squared into 1 minus e to the minus 2s into 1 minus 2s plus 1 e to the minus 2s. Any questions so far? None so far, okay. Okay, so now let's look at some initial value problems then, right? Where we're dealing with the differential equations, finding the Laplace transform. So consider initial value problem A y double prime plus by prime plus cy is equal to ft, where your initial conditions y naught and y prime naught are both 0. Suppose that the transfer function of this system is given by phi s equal to 1 over 2s squared plus 5s plus 2. What are the constants A, B, and C? If ft is e to the minus, you determine fs, right? Ys and yt. Okay. So now we remember last time we recall how to write the transfer function, right? So you have a function here in terms of y and a function here in terms of two functions in terms of t. One with y and one with f, right? So taking the Laplace transform of both sides. So if we take the Laplace transform here, right? Remember this y double prime will be s squared ys, right? Plus, let me just write it here, s squared ys minus sy naught minus y prime naught. And then for this part here, the Laplace transform of y prime will be s ys minus y naught, right? But when we deal with the transfer functions here, in terms of initial value problems, the initial conditions are all 0. You understand here? So y naught is 0, y prime naught is 0. So this here will be 0. So this will drop out. This here and this here will both be 0. So that will drop out. So from this part here, the y double prime, all you will get is y squared ys, which is this term here. And remember, you have a in front of it. From the by prime, you'll just get this here, s ys, and you have your b in front of it, your constant. And the c prime, sorry, the cy, you will get cys. And of course, the ft, the Laplace of that is capital Fs, right? So we could look at the left-hand side here and we could factor out the ys. So you'll get as squared plus bs plus c is equal to fs. And remember that the transfer function here is ys over fs. The left-hand side over the right-hand side. So if you look at this carefully here, right, you'll have to take this fs and bring it to the left here. So it will have to come down, right? So if this comes down to the left here, you'll have to divide it by the left. And then you'll have to divide this here by the ys on the right. Right? So it's basically like you're cross multiplying. So you'll get ys over fs is 1 over a s squared plus bs plus c. And now we could just match up this here and what they give us here in the problem by identification. So the coefficient are s squared here because you have 1 over 2s squared plus 5s plus 2. So your a here have to be 2. Your b have to be 5. And your c have to be 2, right? So that is how you do it there. Part B now, they give us our function ft as e to the t. So therefore, we could take the Laplace of that. Fs would be the Laplace of e to the t, which is 1 over s plus 1. Right? And then from this formula here, we know that ys now, right, is just a cross multiply here by fs. So it's phi s by fs. And what is phi s? Phi s is 1 over 2s squared plus 5s plus 2. And when you multiply that by fs, you will multiply it by 1 over s plus 1, which is 1 all over s plus 1 into 2s squared plus 5s plus 2. Right, so now in order to find your ys, right, well, we have our ys here, but remember we want to work out the inverse, right? So we want the yt. So we have to decompose this into partial fractions. Remember the rule here. The 2s squared plus 5s plus 2 could be factorized into 2 simple factors, 2s plus 1 and s plus 2. So you basically have 3 simple factors in the denominator here. So the rule here is a over s plus 1 plus b over 2s plus 1 plus c over s plus 2. And then now you multiply throughout by s plus 1, 2s plus 1, and s plus 2. So which means you'll get 1 is equal to a into 2s plus 1 by s plus 2 plus b into s plus 1 by s plus 2 plus c into s plus 1 by 2s plus 1. And then if you put s equal minus 1, this term, the second and the third terms will vanish. So you'll end up getting minus 2 here plus 1. So that'll be what? Minus 2 plus 1 is minus 1. And here you will get 1, right? So that'll be minus a is equal to 1. So a is minus 1, right? So when we put s equal minus 1, we could find a equal minus 1. Then when we put s equal minus a half, this term here will drop out because this will be 0 and this last term here will be 0. So the middle term will survive. So minus a half, think about that. Work it out mentally. Minus a half and minus a half. So here you get a half inside this first bracket. Minus a half plus 1 is a half. And 2 minus a half is what? 3 over 2. So that is 3 over 4. Right? 3 over 4 by b, look at here, is equal to 1. So b is 4/3. And then if you put s equal minus 2, this middle term, because this will be 0, and this first term will drop out. So here minus 2 plus 1 is minus 1. Minus 2 by 2 is minus 4, plus 1 is minus 3. So you'll get plus 3c then is equal to 1, so c is our third. So this is the partial fraction here, minus 1 over s plus 1 plus 4 over 3 into 2 s plus 1 plus 1 over 3 into s plus 2. And your yt now is your Laplace inverse of the right hand side. So you could pull out the minus Laplace inverse of 1 over s plus 1, right? 4 over 3. And then here now, you could pull out the 2. So inside here, you'll get s plus a half, right? So I pull out the 2 on the bottom here. So that is 4 over 3 by 2. Laplace inverse of 1 over s plus a half. You can evaluate the Laplace with this 2s here. You can evaluate the Laplace with something over s plus a constant. And plus 1/3, the Laplace inverse of 1 over s plus 2. Right? So this here would be minus e to the minus t. This is 4 over 6, which is 2/3 e to the minus a half t plus 1/3 e to the minus 2t for t greater or equal to 0. Right? So that is the initial value problem. So we have another initial value problem here. Right? So a y double prime plus by prime plus cy equal ft, and our initial conditions are 0 again. Suppose that an input function ft is equal to t when applied to the above system. So remember the ft is your input and the yt is your output, right? Yt is 2 into e to the minus t minus 1 plus t into e to the minus t plus 1. What is the system transfer function? What will be the output if the Heaviside unit step function ft is equal to ht is applied to the system? Right? So we want to find the transfer function. So first of all, ft is equal to t. So which means fs is the Laplace transform of t, which is 1 over s squared, right? So this is your yt. 2 into, you could expand this, you could write ye to the minus t minus 2 plus te to the minus t plus t. Right? So look, we taking the Laplace of that. So we taking the Laplace of 2e to the minus t minus 2 plus te to the minus t plus t. And remember here now, we could treat this here, use the linearity property, pull out the 2. So the Laplace of e to the t minus 2 the Laplace of 1 plus the Laplace of te to the minus t, right? And then plus lt, right? So the Laplace of e to the minus t is 1 over s plus 1. And then you have to multiply that by 2, so you have 2 over s plus 1. The Laplace of 1 is 1 over s, so it's minus 2 over s when you multiply by 2. Here you're using your shift property. So remember the Laplace of t here is 1 over s squared, right? But this here, your shift here is 1, right? So you have to add the 1 here there. Since this here is minus, you add the 1 here. So that will be s plus 1 squared. And the Laplace of t is 1 over s squared. So we could clean up this a bit here, right? And our LCM will be s plus 1 squared by s, right? So which means you have to multiply this here by the 2 have to multiply by s plus 1 by s squared. So you get 2s squared into s plus 1. The minus 2 have to multiply by s into s plus 1 squared. The 1 here have to multiply by s squared. So you get s squared. And this here, this 1 here have to multiply by s plus 1 squared. So when we expand this out here, we get 2s cubed plus 2s squared. You know, it's always good to write it out so you will see what's happening, right? This will be s squared plus 2s plus 1. So you get minus 2s cubed minus 4s squared minus 2s plus s squared plus s squared plus 2s plus 1. So look at all these terms canceling, the first and the third, right? Minus 4s squared, and you have s squared and s squared, like 2s squared, and then another 2s squared. So those will cancel as well, right? And the minus 2s here and the plus 2s. So all you end up with is 1 over s squared into s plus 1 all squared, right? And we know that the transfer function here is what? Ys over fs, right? So this is your ys, and your fs is 1 over s squared. So that will just be your invert and multiply, so you get 1 over s plus 1 squared. Right, so take your time there and look at it carefully. Make sure you follow it. So part B now, what will be the output of the Heaviside unit step function? Ft is equal to ht if it applied to the system. So replacing Ft by ht, right? So if Ft is ht, then the f of s would be 1 over s. Right, remember that? Because, let me just write this here, h t minus t naught. The Laplace of that is e to the minus s t naught over s. Right, so if the Laplace of h t minus t naught, right, is e to the minus s t naught over s, and you just have ht, it means that t naught here has to be 0, right? So the Heaviside h of t means that is interpreted as your t naught here is 0, right? So if your t naught is 0, you have e to the 0, which is 1. That is why you get here, f of s is 1 over s here. So that is an important thing to remember. Yeah? H of t is always 1 over s. Since t naught is 0, right? Right, so you see, look, I wrote it here as well. So you have ys is equal to your transfer function by fs, right? So that will be, this is the transfer function here, 1 over s plus 1 squared, right? And you're multiplying that by fs, and fs is 1 over s. So you're multiplying this by 1 over s. So obviously you will get 1 over s into s plus 1 squared. And now if we want to evaluate the Laplace inverse yt, we need to find, we need to break up this in partial fractions. So 1 over s into s plus 1 squared will be a over s plus b over s plus 1 plus c over s plus 1 squared, right? Because this here is a double, a repeated simple factor, so you have to write it as b over s plus 1 c over s plus 1 squared. And then if you multiply throughout by s plus 1 squared, you'll get a by s plus 1 squared plus b by s into s plus 1 plus c by s. And then we collect coefficients s squared, s, and s to the power 0. A plus b is the coefficient of s squared. 2a plus b plus c is the coefficient of s. And a is the coefficient of s to the 0. So it means that you don't have no s squared on the left. So a plus b is 0. 2a plus b plus c is also 0 here, and a will be 1 when we equate coefficients, right? Now, if a is 1 and a plus b is 0, it means that b is minus 1. And then we could substitute for a and b in the second equation there, and we'll get 2y 1 is 2 minus plus b, which means minus 1 plus c is 0. So c is minus 1. So 1 over s into s plus 1 squared is equal to 1 over s minus 1 over s plus 1 minus 1 over s plus 1 squared. So the Laplace inverse would be the Laplace inverse of 1 over s yt minus the Laplace inverse of 1 over s plus 1 minus the Laplace inverse of 1 over s plus 1 squared. So the Laplace inverse of 1 over s is 1. The Laplace inverse of 1 over s 1 over s plus 1 is e to the minus c. So you have minus e to the minus c. And the Laplace inverse of 1 over s plus 1 squared is t e to the minus t. Right? So you minus that here because you have a negative sign for t greater or equal to 0. Consider the initial value problem again. So we're looking at a number of these problems here involving the transfer function. Consider the initial value problem. So again here with these transfer functions, the initial conditions will always be 0. So y naught is 0, y prime naught is 0. So therefore your Laplace of y double prime plus the Laplace of y prime plus ys, plus the Laplace of y equal the Laplace of f of t. And here now they're giving you f of t is a periodic function with period 2, right? So it's defined to be 1 between 0 and 1, and between 1 and 2 is defined to be 2. Between 1 and 2 is defined to be minus 1. Right, so determine the system transfer function phi s and determine ys. Right? So they just want the Laplace transform of ys. So now we take the Laplace transform on both sides, so we get, since the initial conditions are all 0, then the Laplace y double prime will be s squared ys. The Laplace of y prime will be sys, and the Laplace of y will be just ys. The Laplace of ft is fs. And we know that the transfer function here is ys over fs. Right? The output function over the input. Your output is your y function, and the input is your f function, right? So we have here, if we factor the ys here, we have s squared plus s plus 1 is equal to fs, right? So ys over fs, right? So you bring this down here and you bring this on the right down. So if you move the fs, cross multiply it underneath here now, and you cross multiply s squared plus s plus 1, On the right hand side, you'll end up with 1 over s squared plus 1 over s squared plus s plus 1 is equal to ys over fs. So your transfer function is this here, 1 over s squared plus s plus 1. So part B, you want to find ys, right? So you want to find, remember, this function is defined only between 0 and 2 because it's periodic with period 2, right? So you're taking the integral between 2 and 0, e to the minus s t by ft. So you need to break it up into the integral between 1 and 0, where it's defined to be 1, right? And the integral between 2 and 1, where it's defined to be minus 1. So yeah, that is why I pull out the minus here. So it will be e to the minus st dt minus e to the minus st dt. And the first limit here will be between 1 and 0, and the second limit here between 2 and 1. So this is common. This is very common now. We're doing this over and over. E to the minus st. You integrate that, you'll get minus e to the minus st over s. And you're evaluating that between 1 and 0, and then you're subtracting e to the minus st over s, and the limit would be between 2 and 1. So from the first part here, right, if you put in the lower limit, you get minus e to the 0 over s, which is 1 over s. If you put in the upper limit here, you get minus e to the minus s over s, right? And you could pull out this negative here, so you'll end up with plus. So you get e to the minus 2s over s, which is this term here. And then subtract e to the minus s over s, right? And if you look carefully, this term here and this term could combine. So a minus and a minus, you have 1 over s minus 2 e to the minus s over s plus e to the minus 2s over s. And if you look at the top term here carefully, this is really 1 minus e to the minus s squared. Because if I multiply this, I will get back. This is like a binomial, right? And when you square a binomial, you'll get back. You have to multiply the two terms and double it, you'll get your middle term, you square your first term, and then you square your second term, so you'll get back this here. So fs is 1 minus e to the minus s squared over s, right? Into 1 minus e to the minus 2s. Remember, since it's periodic, you have to take this here and you have to divide it by 1 minus e to the minus 2s because the period is 2, right? And then this denominator here, this is the difference of 2 squares, right? So you could write this as 1 minus e to the minus s into 1 plus e to the minus s. And then this part on top is squared, so you have 1 minus e to the minus s into 1 minus e to the minus s, and these two could cancel. So you'll end up with 1 minus e to the minus s over s into 1 plus e to the minus s. So your fs now, your ys would be the transfer function by fs. The transfer function here is this 1 over s squared plus s plus 1. So you're just multiplying this here by 1 over s squared plus s plus 1. So you end up with 1 minus e to the minus s over s into 1 plus e to the minus s into s squared plus s plus 1. So this is your ys here. Now they didn't ask us to find yt. So just take a look at it there and see if you follow everything so far. Right? And I'll just pause for a few moments just for you to grasp what we did so far, and then we'll continue. Any questions so far? Yeah. Okay, so we'll continue here again. So we consider the initial problem, value problem. Now notice this one have a third order differential equation in it, right? So don't let us confuse here. You have y triple prime minus 4y is equal to e to the t plus t. And you have your initial conditions here. Now, since you have a triple prime here in it, the initial conditions will have to have up to a double prime in it. So you have y naught, y prime naught, and y double prime naught will all be equal to 0, right? Now remember, when you take the Laplace here of this y triple prime, you'll get s cube, sorry, s to the power 3 ys, and then all the other terms will become 0. So you'll get s cube ys minus 4ys. And then you take the Laplace of the right-hand side, the Laplace of e to the t is 1 over s minus 1, and the Laplace of t is 1 over s squared. So on the left-hand side, now you factor out the s cube minus 4, right? Ys is equal to 1 over s minus 1 plus 1 over s squared. So therefore, you know how to divide both sides by you divide the right-hand side by s cube minus 4, right? So you have 1 over s minus 1 into s cube minus 4 plus 1 over s squared into s cube minus 4. So the LCM here will be s squared, s minus 1, s cube minus 4. So you'll have to multiply this 1 here by a s squared, which is this term here. And you have to multiply this 1 here by s minus 1. So your transfer function would be ys, which is this here over fs. So you have fs is s squared plus s minus 1 over s squared into s minus 1, right? Oh, I get the fs. That is this part here. This part is your fs. Remember this here, the LCM is s squared by s minus 1 right? So if you have s squared into s minus 1 here, then you'll have to multiply this side here by s squared, and then you have to multiply the other side by s minus 1. That is why we get this down here, right? So your ys is, your transfer function phi s is ys over fs, where fs is this here. So our ys was this part here, s squared plus s plus minus 1 over s into s minus 1 into s cubed minus 4 divided by s squared plus s minus 1 over s squared into s minus 1. And then when you invert and multiply, right, you see how easy this cancel, right? You'll end up with this term here going on top, right? And canceling with these two here. So you'll end up just getting s cube minus 4 at the bottom, and then this s squared plus s minus 1 will cancel with s squared plus s minus 1. So your transfer function is 1 over s cube minus 4, right? And then they wanted us to find ys, right? But we already did that already, right? So that was already found from part A. Right. So apparently I did part A, part B and part A, right? But I could have done it differently, where I could have just find fs and then rearrange the equation to find transfer function, but like we did in the previous example. And then now we would have had to do all the work now in part B to find ys, right? Solve the initial value problem. Y prime plus y is equal to 2 plus the Dirac delta function t minus 1, where the initial condition y naught is 0 and t lies between 6 and 0. Graph the solution on the indicated interval, right? So now we want to solve this problem here. So we have to take the Laplace on both sides of the equation. So taking the Laplace transform on both sides gives us what? The Laplace transform of ys is sys plus is sys. Let me go back to my blue ink here. Right. The first derivative, the Laplace transform of that is minus y naught. Right? But the y naught here is 0, so that part drop out. So that therefore this part drop out, right? And then you're taking the Laplace of ys, and then you're taking the Laplace of 2 over s, and then the Laplace of the Dirac delta t minus 1 is e to the minus s, right? So now here, the left hand side, we factor out s minus, we factor out the ys, and we have s plus 1. The right hand side, we have 2 over s plus e to the minus s. So we divide the right hand side by s plus 1. So ys is 2 over s into s plus 1 plus e to the minus s over s plus 1. Right? Now, to evaluate this part here, we need to use the partial fraction decomposition. So 2 over s into s plus 1 is a over s plus b over s plus 1. So when we multiply by s plus 1, we'll get a2 is equal to a into s plus 1 plus bs. And if we put s equals 0, right, we have a equal 2. If we put s equal minus 1, we have minus b is 2. So which means b will be minus 2. So therefore, ys becomes 2 over s minus 2 over s plus 1 plus e to the minus s over s plus 1. So we take the Laplace inverse. 2 by the Laplace inverse are 1 over s minus 2, the Laplace inverse are 1 over s plus 1 plus the Laplace inverse are e to the minus s by 1 over s plus 1. So in the first instance here, the Laplace inverse of 1 over s is 2. Sorry, it's 1, and then you have to multiply it by 2, right? The Laplace inverse of 1 over s plus 1 is e to the minus t, and then you have to multiply it by minus 2. And the Laplace inverse of 1 over s minus 1 is e to the minus t. But since e to the minus s there, that our t naught is minus 1. Therefore, based on the definition of the inverse, when you have a Heaviside function here, would be h at t minus 1 into e to the minus t minus 1. So now we could define this Heaviside, right? Because the inverse here gives us a Heaviside. The third part here gives us a Heaviside function. So remember, this here will be 0 for t less than t naught, right? So your t naught here is 1. So when t is less than 1, this is 0. So this part, if this is 0, then the function will just be this part here alone. 2 minus 2 e to the minus t. And when t naught, when t is greater or equal to t naught, this part here is 1. So you'll get 2 minus e to the minus t plus e to the minus t minus 1, right? Which is this part here. 2 plus e to the minus t by e to the 2 plus e minus 2 in bracket e to the minus c. When you multiply this out, you'll get back this here, right? And then they want us to graph it. So if you're graphing this here, right, this is the first part here up to 1 here. This is how the graph will, the formation of the graph. So what will happen here? This 1 here will be an asymptote, right? Because it is going up. Sorry, 2 will be a horizontal asymptote because here the graph stopping at, it's not reaching up to 1, but from 1 here now, this is the graph here defining like this. So in other words, 1 is like a vertical asymptote and 2 is a horizontal asymptote. From 1 and beyond, this is how the graph will, the shape of the graph. So 1 is a vertical asymptote and 2 is a horizontal asymptote. T equal 1 is a vertical asymptote and y at t equal 2 is a horizontal asymptote. Solve the initial value problem. Y double prime delta Dirac delta t minus 1 minus the Dirac delta t minus 3, where our initial conditions here are both 0 and t is between 0 and 6. Graph the solution on the indicated interval. So the left hand side here you get s squared ys, because remember the initial condition is 0. The Laplace of the delta Dirac t minus 1 is e to the minus s, and the Dirac delta t minus 3, the Laplace of that is e to the minus 3s. So you'll end up getting ys is equal to e to the minus s minus e to the minus 3s over s squared, right? So the take the Laplace of that is just to find yt, rather to solve the problem here, the initial value problem. You're taking the Laplace inverse of e to the minus s over s squared minus the Laplace inverse of e to the minus 3s over s squared. And this will be the heavy side t minus 1, t minus 1. And this one here will be the heavy side t minus 3, t minus 3. Right? Now remember, the heavy side function, your t naught here is 1 and your t naught is 3. So first of all, we could break up yt into 3 regions, right? Where t is between 0 and 1, right? So anything less than 1, this is 0. And this is 0, right? So 0 minus 0 is 0. So that is how the function defined between 0 and 1. It's piecewise, so it's 0. Now between 1 and 3, how the function defined? Well, h at t minus 1, that will be 1. But this will be 0, right? So h at t minus 1 is 1. So 1 by t minus 1 is t minus 1, right? This part here will be 0. And then beyond 3, both of them, both heavy sides will be 1. So you get t minus 1 minus t minus 3. T minus 1 minus t minus 3. Right? You notice the t's will cancel and you get minus 1 plus 3 is 2. So the function between 3 and infinity is defined to be 2, right? So this easy to sketch, right? Between 0 and 1 is 0. So this is your ft axis here. And this is your t axis here. Sorry, your yt. Could I have it in terms of y here? Right? So t minus 1 between 1 and 3. Your gradient is 1. And then between 3 and infinity, the graph is 2. Solve the initial value problem once again, right? So we're doing a lot of practice here with all these different functions here, right? Periodic functions and delta Dirac functions involving initial value problem, heaviside functions, and the transfer function, right? So this work is going a little beyond what you'll be doing in the coursework exam, but this is in preparation for your final exam, right? So you need to really do this and focus on it as well. Solve the initial value problem, y double prime minus 2y prime is equal to the delta Dirac, or the Dirac delta t minus 1, right? At this time here, your initial condition here, one of them is 1 and the other one is 0, right? And graph the solution on the indicated interval. So Your y double prime, you have to write it out, s squared, the Laplace of that. So we taking the Laplace on both sides. You know the Laplace of the Dirac delta t minus 1 will be e to the minus s. The Laplace of y double prime is s squared ys minus sy naught minus y prime naught. And the Laplace of y prime is sys minus y naught. But you have to multiply it by -2. So you'll get minus 2 sys, and a negative by a negative is plus 2y naught. Right? So your y prime naught, this term here go drop off. This term here will be minus s, because this is 1, right? And this term here will be 2. You seen it here? Because y naught is 1. So you have s squared ys minus s minus 2 sys plus 2 is equal to e to the s. So we carry the minus s and the plus 2 on the right hand side of the equation. Right? So we have s squared minus 2s in bracket ys, you factor out the ys and you carry the s on the right hand side, so you get plus s and -2 plus e to the minus s. And then you divide ys by s squared minus 2s, so you'll get s minus 2 plus e to the minus s over s squared minus 2s. And then this here, the denominator you could factor out a s, so you have s minus 2 plus e to the minus s over s into s minus 2, and then you could break up this into partial fraction. So 1 over s into s minus 2 is a over s plus b over s minus 2. Multiplying throughout by s minus 2, you'll get a into s minus 2 plus bs. And when you put s equal 2, you'll get 2b is 1, so b is a half, and s equals 0. You'll get minus 2a is 1, so a is minus a half. So remember, you have s minus 2 plus e to the minus s in the numerator, which is, you could break up as s minus 2 over s into s minus 2 plus e to the minus s over s into s minus 2. So this here will give me the s minus 2 will cancel, you get 1 over s plus e to the minus s over s into s minus 2. And remember, the a was minus a half and the b was a half. So all you have to do now is pull out the e to the minus s, pull out a half, because a half is a common factor. But since this term here is positive, you swing it around. So you put 1 minus s minus 2 at the front, and then you put this term here minus 1 over s at the back. So you'll get a minus a half 1 over s, and your plus a half 1 over s minus 1. But remember, you have to multiply by e to the minus s. So your ys is 1 over s plus a half e to the minus s over s minus 2 minus a half e to the s over s. And the next step now is to take the Laplace inverse of 1 over s plus a half the Laplace inverse of e to the minus s over s minus 1 minus a half the Laplace inverse of e to the minus s over s. So the first one here will just be the Laplace inverse of 1 over s is 1 plus a half the heavy side t minus 1 e to the 2 into t minus 1, and then minus a half h t minus 1. Right, so anytime the t is between 0 and 1, this will be 0, and this will be 0. So these two terms will drop out, so the function will just be 1. When t is between 1 and 2, right, this will be 1, and this will be 1. So you'll get 1 plus a half e to the 2t minus 1, right? Minus a half, and 1 minus a half is a half. So you end up with 1 plus a half e to the 2t minus 2. Right? So from 0 to 1, the function will be this here. And then after between 1 and 2, it will be a half plus a half e to the 2t minus 2. So you'll have an exponential growth here then. Right? And it will go somewhere to a little beyond 4. Right? Because this part is exponential. If you plug in 2 here, you will see that e to the 2 by a half plus a half, you'll get a little more than 4 point something, right? So this is the shape of the graph here. Solve the initial value problem. Y double prime plus 2y prime plus y is the Dirac delta t minus 2, and you have y naught is 0 and y prime naught is 1, and you have t between 0 and 6. Graph the solution on the indicated interval. Taking the Laplace transform of both sides to obtain s squared ys minus sy naught minus y prime naught is equal to 2sys minus 2y naught plus ys is equal to e to the minus 2s. And now substituting the initial conditions, right? So your y prime, this part will drop out, right? Sorry, that part won't drop out. The part with the y naught will drop out, right? So this part here will drop out, and this part here will drop out. This part here will be 1, right? So this here is 1, right? So you will have, you factor out your ys. So you'll have s squared plus 2s plus 1 ys, and then you have your minus 1 here is equal to e to the minus 2s. You carry your minus 1 across, so you'll get 1 plus e to the minus 2s, and then you divide by s squared plus 2s plus 1, which is s plus 1 squared. So your ys is 1 over s plus 1 squared plus e to the minus 2s s plus 1 squared. And now you take the Laplace inverse of s plus 1 over s plus 1 squared, that is t e to the minus t, using the shift property. And similarly, Laplace inverse of e to the minus 2s would be the heavy side over s plus 1 squared. The heavy side at t minus 2 e to the minus t minus 2. And when t is between 0 and 2, the heavy side is 0. So you'll just get t e to the minus t. And when t is greater than 2, less than or equal to 6, this is 1. So you'll get t e to the minus t plus t minus 2 e to the minus t minus 2 in the exponential position, right? So this graph here between 0 and 2 will be something like this here, right? You'll go up reach a maximum, and then come back down here to 2, then go back up here somewhat, right? And then, so from this part here between 2 and 6, it will go up, form a maximum, and then come down here. And then here you will have a turning point here, and then it will just go towards the value 6 here as it declines somewhat, right? So that is the graph there of that function. Right, so these are problems here that are very important that you need to address, right, in order to go forward. So what would happen now is, right, so from the next day forward now, we'll be going through the last part of the lecture, which involve the initial value and final value theorems, right? So that is the last thing we have to do, the initial and final value theorems. And then we have to do some more problems with transfer functions and finding the Bode plot when you have a transfer function, finding the zeros and the poles and so on, right? So you have to know how to sketch that. So we look at some of that in the next session, as well as we look at some questions again, you know. So we basically have like 2 sessions again, Friday and Wednesday, and then next Friday, you have your midterm exam between 1 and 3. So remember to keep going over your work up to page 67. You'll be tested for the midterm exam. Let me once again say that it will be a combination of multiple choice and numeric answers. So when you go on, click online between the time and you log in, it will be problems of a similar nature to what you did in the last midterm, and you'll have to work out these problems manually to come up with the answer, right? So you have to be able to practice and make sure you get these the hang of doing things like that, right? Because you wouldn't want to make errors and end up getting the wrong answer, because you wouldn't get any partial marks to these questions. So you have to be very careful, right? So again, let me wish you the best, and thanks for attending, and I'll see you again on Friday, right? So on Friday, we'll continue the lecture, and then we'll go into some more problems again, right? Hopefully next week, I might be able to look at maybe a pass exam or 2 final exam, once time allows, right? So take care, thanks for attending, and I'll see you again next on Friday. Any questions? Right? No questions? Okay then, well, we could end here, right?